Hi guys, this is meant to be just a short video to kind of summarize the things that we talked about in class last time. All right, so we talked about a bunch of the different ways, different reasons why sounds sound different. The first thing we did is I handed out tuning forks in class, and the tuning forks were different sizes and shapes. They had different frequencies, and you were allowed to play around with them a little bit. You were able to smack them and listen to them. And some of the things that we came up with is, number one, that tuning forks of different frequencies played different notes. All right, so the first thing is that tuning forks of different frequencies play different pitches. And so why do different sounds sound different? Well, one of the reasons is because if it has a different frequency, it plays a different note. The other thing you notice is that when you hit it a little bit harder, that it's louder. Okay, now what hitting it harder does when you hit those tuning forks and you smack it harder, it causes it to vibrate more. Now, more vibration, if you've watched the video on what is sound, remember sound comes from vibrations. And so if the tuning fork is vibrating more, it still has to have the same frequency, right? We noted that when we hit it harder, it still played the same note, it's just it was louder. And so the frequency couldn't change, but what did change was how far the fork was vibrating. That's the amplitude, right? Amplitude is how far is it moving from that central position. The tuning fork was here, and then it vibrates like this. So how far does it go? So it's the amplitude. So the second thing we discovered is that amplitude affected the volume. All right. Now, those are two things that we've talked about with respect to waves before. We then talked about how velocity is connected to frequency and wavelength. We recognize that different frequencies all have to travel the same speed. And we didn't really do an experiment here. We just recognized that if we play two notes at the same time on, for example, the piano, you hear them both at the same time, right? You don't hear notes at different times because they're different frequencies. So frequency can't affect the speed. The speed of that sound wave getting from that thing to your ears has to be the same no matter what the frequency or wavelength is. And so therefore, we said, well, the speed must be the same for a given medium. Now, we do know that in different mediums, solid, liquid, gases, even different temperatures and humidities and things, those things will affect the speed of sound. But by doing that, you've effectively changed the medium. So for a given medium, air, the speed of sound should always be the same. Now, if the frequency is different for each note, but the speed is the same, that must mean that the wavelength has to change, right? We noted in previous videos that the speed is equal to frequency times wavelength. And so if the frequency is going up, but the speed is staying the same, then the wavelength must go down. They're inversely proportional. All right, so that'll be something important. The higher your frequency, the faster, the more often you have cycles being completed. It must mean that you have shorter waves there. That'll be something that we see in the future. All right, so that's what we got from the tuning fork lab. Let me just summarize really quick. Tuning forks, frequency determines pitch. Amplitude determines volume. We followed that up with another question, which was, well, why do different sounds, why do different instruments playing the same note sound different? Or for that matter, why do people singing the same note sound different? If all it is a simple wave, why is it that different things making the same note all sound different? And so that was the next question that we tried to answer. This question, that is what we call timbre. Timbre is kind of the texture or the feel of the note. And we had to answer another question first. And the question that we needed to answer is, what happens when waves run into each other? When you have two waves, whether they're going against each other or at the same time of each other, what happens to those waves? And so we did that with a slinky, and we sent a slinky down. The first thing that we noticed is that when two people sent waves down at the same time, if those waves ran into each other, one thing that happened is they kept moving. Okay, after they ran into each other, they kept moving. In the moment that they ran into each other, instead of just having two small waves on top of each other, we ended up with one big wave that then eventually disappeared as the two waves continued on. All right. If that's hard to picture, then ask me next time you're in class and I'll show you using the slinky in class. But that's something called constructive interference. Constructive interference says that when two waves run into each other, if they're both on the same direction of your slinky, or if they're both on the positive side of your line, then they're going to add together to become a larger wave, to have more amplitude. That kind of makes sense. When you play two speakers, you get a larger volume. And why do we get larger volume? Because when those two waves add together, you get a larger amplitude, right? Now, the opposite can happen as well. And the opposite is if two waves run into each other and one of them is positive and the other one is negative, two pulses run into each other, they can actually cancel out. And that's called destructive interference. And if you'll look on Classroom, Google Classroom, I posted a video of me sending two waves against each other. And you can see in the slow-mo video that they actually do cancel each other out just when they overlap. But then they just keep on moving like they did before. That's a really interesting property of waves. We call it superposition. Superposition is the property that when two waves run into each other, we can add their amplitudes together. If the amplitudes are in the same direction, they add together and get bigger. If they're in opposite directions, we kind of add that positive and negative together to kind of cancel out a little bit. All right. So that's the principle of superposition. So both the constructive interference and the destructive interference both are part of that superposition property of waves. And all waves show this property of superposition. All right. So we can actually see this. Let me show you why this is important. First, just for your personal reference, the speed of sound in air, normal air, 20-25 degrees Celsius, is 343 meters per second. And that's the number that we'll use in class. You'll notice that it's about a third of a kilometer every second. So it's pretty fast, but not as fast as light, as we know from our experience with lightning, where we see the light first and then we hear it later on. All right. Now, the question about what happens when they run into each other, we just talked about the demo of the spring slinky. And we talked about superposition. When two waves run into each other, the result is the vector sum of their original waves. We say vector sum because the direction matters. If they're both up, they add together. If one is up and one is down, they cancel out. If they're both down, then they add together down below. So that's our constructive and destructive interference. I will show you the demo of the two speakers in class the next time. I don't have two speakers, so I'm hoping a couple of people volunteer to bring speakers to class on Sunday. So timbre, this is what we were talking about before. Timbre is when we mix together a couple of waves and they build on each other to create something a little bit different. Let me demonstrate. Let me show you. This is what an A would look like. Okay, this is the A that when you're in band or orchestra, this is the A that they play to tune to. And it's a very pure pitch, right? It gives you a very specific tone, and that's what you're tuning your instruments to, this 440 hertz. And the wave is a nice, perfect tune, like nice, perfect wave like this. We call it a pure tone. Now, any other instrument that plays an A like this, it's not going to look nice and pretty. A clarinet playing an A looks like this up here. And you can still see it goes up and down and up and down and up, and it does still have that periodic nature. And the frequency going from one peak to the next will still be 440 hertz. But you can see that due to the makeup of the clarinet, there's lots of different waves that are inside of that clarinet that kind of build together. Some of them add together, some of them subtract. But this idea of superposition happens, and the wave changes its shape because of the way all of these waves are combining. It looks a little bit different than the trumpet, which we can see down here at the bottom, which again has exactly the same frequency, the same wavelength, but the waves created in a trumpet, due to the shape and size of a trumpet and the materials that it's made out of, are very different from the wave that's created in a clarinet. Again, the frequency is going to be 440, which is going to give us a pitch of an A, but it does mean that it's going to sound a little bit different. A human voice is even more different. Okay, this is a human voice speaking and whispering, This is somebody making the A sound, and this is somebody making the O sound. And you can see how a frequency might be kind of consistent, but there's different little jumps and jags. That's because of your vocal cords, right? Everybody's vocal cords are a little bit different. And when your vocal cords are a little bit different, they're going to create slightly different waves building and destructing on each other, just like we saw with the trumpet and the clarinet there. And so the reason why different sounds or different voices sound different in terms of, even though the note is the same and even though the volume is the same, you get a different kind of texture or flavor of that sound, that note, because of all of these different waves that are being created. Your vocal cords or the instrument will create what we call that principal tone, but then it will also create other smaller overtones and undertones that then build on each other to create these stranger waves that overall still have the right frequency, so we still hear the right tone, but it changes the feel or the sound of that pitch. All right. So I hope that was helpful. I hope you have a better idea now of why different sounds sound different. If you have questions about any of this, please just let me know, and I'm happy to answer your questions and hopefully help clarify anything. All right. See you next time.